Hello everyone, this is Dr. Hopkins narrating the next in our video series for Chem 472, and this is a brief discussion of colligative properties. So first of all, we're going to define what colligative properties are, and basically it's a property that of a solution that depends only on the concentration of your solute and doesn't matter what the identity of the solute is. So this is very similar to when we discuss ideal gas mixtures or ideal solutions. So in this case, what we're doing is in every one of these cases with colligative properties, we're going to assume ideal behavior. All right. So our four colligative properties, the first two are related to solution and vapor in equilibrium. The first one we've already seen, which is basically Raoult's law. If we have a volatile material or volatile solvent, we add non-volatile solute. We're reducing the mole fraction of the solvent, so we would automatically reduce the mole fraction of the vapor pressure. Okay, and that's the vapor pressure lowering. The boiling point elevation is so you have an increase in the boiling point. We're not going to derive this, and this is the simple equation you would get in general chemistry if you covered colligative properties. So the amount of the elevation of the boiling point is due to primarily solvent-dependent properties. So if this was water, that would just be a collection of fundamental constants of water and the molality of the solute. So it would only depend on essentially the molar mass and the amount, so the number of moles. And that would be your boiling point elevation. What may be more useful is osmotic pressures. That's the third one we're going to talk about. And this is a colligative property between liquid solvent, liquid solution. If we go down to this figure below, basically what we have is solvent, and we have a solution with the solute, and we have a membrane that will pass the solvent, but not the solute. So let's say the solute's too large to go through. So what that sets up is a situation where we have a concentration gradient across this membrane where solvent can pass. So you're going to have solvent driving into this solution to try to drive the concentration down to the same concentration as the surrounding solvent. So there's a one-way movement which causes a pressure, which is measured as our osmotic pressure. So this is something similar to what you would have with cell walls and a solution outside that have a lower concentration. It would want to drive through the walls. You might end up putting pressure on a particular cell. But anyway, this once again has there's nothing in the equation with respect to osmotic pressure that relates to the identity. It's just the molar concentration of the solute. And R is our gas constant. Okay, so the last one we're going to cover is freezing point depression. We're going to go into a little bit more detail on this one. So basically we have solid and liquid in solution. It's in equilibrium. Now freezing point depression, if you know, in the winter, it's what you do. You add salt to the roads to lower the freezing point of water so that you have water instead of ice on the roads. So that's one use of this. So here we have these in equilibrium. We've set up, just to remind you, the chemical potential of the solution, the liquid solution, is a reference of a pure liquid, and then it's related to the mole fraction. So notice our activity coefficient we're assuming is 1, so we've gotten rid of any non-ideal term to this. Okay, so as it says, the solution and the solid are in equilibrium. We're going to hold this at constant pressure and constant number of moles of the solvent. So we're only going to add solute, not solvent. So we write out the complete expression for the change in chemical potential of either one, but the change in chemical potential of the solution. Then we have a temperature-dependent term, a pressure-dependent term, a solvent, number of moles of solvent-dependent, and moles of solute-dependent term, and all of their corresponding partial derivatives. Two of these are going to go away because we've just said dP is equal to 0 and dNA is equal to 0. Okay, so we're left with just two terms. This partial derivative with respect to temperature is the molar entropy. This partial derivative we can derive using our original definition of our chemical potential. We take the partial derivative, and we're left with a mole fraction of our solute over the number of moles of solvent, which is essentially the number of moles total, because if we're in a dilute solution, the number of moles of solvent is really large, number of moles of solute very small. And we take this a little further, so let's now introduce the molar entropy for our solution dt. So we're going to assume that B only dissolves in the solution. We're not going to consider a co-frozen solid. So the solid side only has dt because there's no solute in that solid side. And so here we have this expression. We can then approximate, because if it's a dilute solution, the entropy of the solution and the entropy of a pure liquid would be the same, which allows us to couple these entropies. And so this is an entropy of fusion. All right, and so we have all our dNB terms on this side, our T terms on this side. And then remember, the entropy of fusion is delta H over T when we discuss that. And so we can substitute that in. We've got minus delta H fusion over T, dt over T, right? And then we're left with this. Now we've simplified this expression. It's, yes, R over N, so total number of moles, so that we're only going, when we integrate this, we're just going to integrate the number of moles of dNB. So this can be constant and pulled out of the expression. And then we evaluate both of these integrals, and we could get how temperature changes to get our freezing point depression. We can also express, and I've left this in here, even though I've not integrated it that way, we can express the change in moles in B in terms of the change in moles of A, or change in mole fraction of A, because anytime you add B, we're changing the mole fraction. Now, freezing point depression, similar to the boiling point depression, gives a simple expression where we have these KFs that depend on solvent properties. So actually there are tables of these constants for various solvents that you can look up. But once again, it only depends on the molality of the solute. It doesn't depend on the identity. So what happens if we allow it to deviate from ideality? So if we allow our activity coefficient to change, we get what are called eutectic mixtures. Okay, so let's start with, now I've rephrased our freezing point depression ideal case in terms of the solvent, not the solute. So the solute is just lowering our mole fraction. And so we can re-express this. This is our integrals. And then if we put it in terms of, this is the change in the freezing point. So that's what the new freezing point is. The old freezing point, or the freezing point of pure A. And then notice we have activity coefficient assumed to be 1. So that's for an ideal mixture. This is still the freezing point depression that we just discussed. Eutectic mixtures, where we put a solute in that interacts strongly with the solvent, it doesn't make any sense that it would be ideal, especially as you raise the concentration. At really low concentrations, even an interaction with the solvent won't reflect, so you can probably assume ideality and get the correct freezing point depression. But if you have a eutectic mixture, you have to deal with this idea that it's non-ideal. And all we have to do is change this equation by adding in the activity coefficient, which is going to be different than 1. And so a eutectic mixture is one that if you put two solids together, you can put two solids together, it will depress the freezing point, and it depresses the freezing point more than what an ideal mixture would. Okay, so until next time.